Now we're going to look at combinatorial constructions where we talk about taking subsets of objects in combinatorial classes to build up new classes. These constructions are more complicated. We didn't cover them in part one. And this is an example where in the lectures we'll work at a level in between what we did at part one and what's in the purple book, where these theorems are just stated improved in a few lines. So we're going to look at two additional constructs. If we have a class of unlabeled objects with their generating function a of z, then we're going to look at two operations, the power set operation and the multiset operation. Power set is of A is the finite sets of objects from A without repetition. And the multiset of A is the finite sets of objects from A with repetition. And then we'll talk about what the generating functions of these things are after I show examples. So power sets, it's the class of all subsets of A. These are examples when A is simply one atom or two atoms or three atoms or four atoms. For example, if I have all the sets of three atoms and I want all the subsets of four atoms, I just take the ones that don't have the fourth one. And then I take that same list and I add the fourth one to it. That gives all the subsets of four atoms. And you've seen this in many different guises before, but it's very clear that the number of elements in the power set of n items is 2 to the n, because each time we're just multiplying by 2. Or just formally that we can use later on to prove about the generating functions. If you want the power set of m items, you take the power set of m minus 1 items, and you take the Cartesian product of that with the empty set plus the mth item. That's what we're doing here. Take the empty set or add the mth item, and that's a lemma of how we construct power sets. Let's look at the generating function. So if we want the power set class for m atoms, that just means pick some out with no repetitions. And so there's a bunch of atoms, each have the generating function z. The generating function for that is sum of every object in the class, z to the size of that object, the number of items in the subset. Or if we use the fundamental identity and collect the ones of size n, then that's also equal to sum n greater than or equal to 0, pmn z to the n, where pmn is the number of subsets of size n for the m atoms. And again, this is very familiar, but let's look how it works formally with the symbolic method. The lemma that I just showed is the construction. It's simply the empty set plus A1 times the empty set plus A2 and so forth times the empty set plus AM. And so that immediately translates to the generating function equation. Since the generating function, each one of these is 1 plus z, and there's m of them, that immediately gives the OGF equation pm of z equals 1 plus z to the m, or the expansion, the number of subsets of size n of m items is m choose n, which is familiar in elementary. So that's power sets. If you take Pm of 1, that's the total number of subsets of m atoms, that's summing on n, Pmn, and that's just 2 to the m. So again, that's going to confirm elementary combinatorics. Multiset is the same thing, except we allow repetitions. A multiset of a single atom is just a sequence of those. Multiset of two atoms is, for each one of those, you can add one B or two Bs or any number of Bs and so forth, if repetitions are allowed. Again, you want the multiset of m atoms. You take the multiset of m minus 1 of them, and then a sequence of the last one. The sequence could be 0, 1, or however many. So that's the construction for multiset. Now we can do the same thing with the symbolic method with the generating functions, and now it's going to be SMN as the number of subsets of size n with repetitions allowed. The construction is just sequences, a cross of sequences of each one of them. And what's the sequence of an atom? The generating function for the sequence of an atom is 1 over 1 minus z. So we get 1 over 1 minus z to the m. The number of atoms, subsets of size n, that's an elementary generating function expansion, is just n plus m minus 1, choose n minus 1. And again, you may be familiar with that from elementary combinatorics. We don't have to do that with atoms. We can do that with any class of unlabeled objects. If you have a class of unlabeled objects with ordinary generating function a of z, and you take the power set of that class, then the generating function of the class that's formed in that way is given by this equation. There's two different ways to represent it. And we'll look at the proof of that on the next slide. Either it's the product for n bigger than 1 of 1 plus z to the n to the anth power, where an is the number of objects of size n in the original class, or it's exponential e to the minus some k greater than 1 minus 1 to k z k over k. We'll look at the proof of that, which is not difficult on the next slide. And similarly for multiset, we have a similar equation where it's 1 over 1 minus e to the n to the an, which is e to that power. We're going to prove this once, but once it's proved, we can apply it in the same way as the other operations that we've done for the symbolic method. These are just quite a bit more complicated in terms of their formula. Let's look at the proof for power sets. Again, the power set of a class that consists of two atoms is just broken out, either empty plus the one or empty plus the other. Another way to write that is 1 plus z to the OGF, the